Hello, this is video 18. In this video, I'm going to go over the second case of projectile motion. We just went over the first case in the previous video. The second case of projectile motion is your projectile is launched at an angle instead of horizontally. This is going to be very similar to the previous case. The only difference is that now that you are launched at an angle, that initial velocity has an x and a y component. 99.9% of the time, you're going to be given the angle with the horizontal axis. So you can go ahead and use cosine for the x component. V initial x equals V initial times cosine, because the x component is adjacent to the angle. And then use the sine for the y component. V initial y equals V initial sine of angle. And then we're going to have the same acceleration as always for projectile motion. Ax is 0 for the x direction. Ay is negative 9.8 meters per second squared for the y direction. As you can see from the picture here, when your projectile is launched at an angle, the velocity, the y component, gets smaller and smaller. It's actually equal to 0 here. And then the y component gets bigger and bigger. This is free fall. Gravity slows down the particle in the y direction and then speeds it up, allowing the projectile to fall back down. In the x direction, you notice that the arrow is always the same exact length because the velocity in the x direction does not change. There is no acceleration in the x direction. A question I like to ask is the velocity 0 at the top of the path? What do you think? Well, it's not 0 because there's still some velocity in the x direction. So don't just be tempted to say it's 0 because it stops in the y direction. It's still moving. It doesn't stop completely at the top of the path. Let's do this example here for a projectile launched at an angle. So this is a two-part problem. So John throws a baseball from the outfield from shoulder height, initial velocity of 29.4 meters per second, initial angle of 30 degrees. So this way, the initial is given here, the angle is given, and then the third baseman catches it at an equal shoulder height level. So it's going to go right back to that same height. This is supposed to be a nice parabola here. What maximum height does the ball reach? We're looking for the maximum height right here. So how do we approach this? Well, as soon as you realize that it's a projectile motion problem, separate the x and the y directions. Write down what you know for each direction. The x direction, we can find the x component of the given velocity. It's going to be v initial, which is 29.4 cosine of 30. And this gives us 25.5. And then we can find the, let's continue with the x direction. We have ax is 0. And actually, and this is sometimes what you might do, but let's stop for a second. Let's go ahead and look at the y direction because it's asking for maximum height, which is a y variable. So we can still use this, but for now let's focus on the y direction. V initial y is going to be V initial sine, 29.4 sine of 30, which is going to be 14.7. And then AY is negative 9.8 meters per second squared. And then we're looking for the maximum height. Well, we talked about in a previous slide that in the y direction, the object stops here because then it goes back down. So we know that VFY is equal to 0 if we split our problem in half. We don't care about what happens in the second half, just when it gets to the maximum height. And now we have three variables. So we can actually find delta x or delta y by using the last kinematic equation. So sometimes we do use other kinematic equations. This is the one that says vfy squared equals v initial y squared plus 2a delta y. We can use this one to solve for delta y. We cross out the vfy squared term, that's 0, and then we solve for delta y. We're going to subtract the voy squared from each side and then divide by 2a. That's going to give us delta y. We go ahead and plug in our numbers. Now you notice in this case the negative does not get squared because it's not in parentheses. So the negative from the acceleration will cancel out this negative as we expect because we're going a positive height. We plug in negative 14.7 squared divided by 2 times negative 9.8. And what we're going to get is 11.0 meters. That's the maximum height. So we didn't do all of this in the x direction for nothing. We're going to be able to use that for the second part of the problem. The second part of the problem says how far is the third baseman from John. So you see that we do need that initial velocity in the x direction, which we found to be 25.5 meters per second. And we know ax is 0. Now you may think, well, we still don't know the time, so we're still not done with the y direction. If we go back and write down the y direction here, we have v initial y, which we found as 14.7. We have v final was 0, but that was when we were looking at the halfway point here, which is okay. We can still look at the first half of the problem. We have ay is negative 9.8. So with these three variables, we can find how long it takes to get to the maximum height. We can use the first kinematic equation, which says vfy equals v initial y plus ayt. Use this to solve for t. We're going to get t equals negative voy divided by ay, and we get 1.5 seconds. Now be careful, don't just say, okay, well now let me use that for the x direction. Always draw a picture and know what you're referring to. This is the time that it takes to get to the maximum height, which is halfway through the motion. But now we're looking for how far is the third baseman. We're looking for this, which is double this time because it's the full motion, and this time was only half of the motion. So we can use the time as double the 1.5 seconds that we just found. And now we know that for the full motion, it takes 3 seconds. Now we have enough variables in the x direction, and we can use our kinematic equation, delta x is v initial x times time, in order to find how far the third baseman is, and I got 76.4 meters. So when you use the time that is common to both directions, make sure that you're talking about the same exact part of the problem as well. The last thing I'd like to do in this video is a your turn problem. I like this one. Usually students have a lot of fun discussing it. A battleship simultaneously fires 2 shells at 2 enemy submarines. The shells are launched with the same initial speed. Notice they do not have the same initial velocity, right? Because one is launched at this angle, one is launched at this angle. I'll draw it on the side here. The picture is not the best, but one has this angle, one has this angle. So the length of the arrows are the same. The speed is the same, but the direction is not. If the shells follow the trajectory shown, which submarine gets hit first? So the idea is that the red one goes up higher, but the yellow one goes further. So you may be tempted to think, well, both at the same time, but that tends to be the answer to a lot of these questions. But actually, that's not the answer. The answer is actually submarine A. The shell that goes Oh, sorry. I was thinking one thing and I said another thing. Which one gets hit first is submarine B. This is because the one that goes higher actually takes more time, and we did a similar one of these problems when we did free fall problems. When you're going higher, then it takes longer for you to get to V equals 0 in order to stop and come back down. So that's the easiest and fastest way I can say it. And you might be wondering, well, what about the fact that the yellow one goes further? Doesn't that take more time? Well, no. The yellow one got there faster, but it traveled further, but it still didn't travel as long of a path. If you look at the whole path, the red one still traveled a much bigger path. The red one took longer because it went higher, and so it took longer to stop, and then it had to still fall all the way back down. So hopefully that was clear, and this ends the video for the second case of projectile motion, which was very similar to the first case of a horizontal projectile. The only difference is that you had to find the x and y components of that initial velocity before you separated the problem into two separate one-dimensional problems.